writing over there in a second. Got it? All right. I'll begin with a word of prayer. Dear Lord Jesus, we thank you for this morning. Thank you for these students. Pray to be with us today. Help us to glorify you, Lord, in what we do. And I just pray that you would help these students to continue working on this class and others this semester, Lord, that they would just have perseverance to do their best, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so we are now in Chapter 3, which is on line integrals and harmonic functions. And so if you don't mind, I'd like to say some words and not write anything down because these things are better read than written. So a path, we're going to study paths and curves in here. A path is simply a continuous function from some subset of the reals into the complex numbers for us. If we have the path so that it doesn't self-intersect, if the values of the path don't come back to the same point for different parameter values, it's said to be simple. All right. So a simple path is one that's not intersecting. If the path begins and ends at the same point, it's said to be closed. All right. So a simple closed path is one that doesn't intersect except for that one point where it loops back together. Okay, so that's a simple closed path. Then we also like to talk about what's called a curve. So a curve in Gamelin is what would sometimes be called a piecewise smooth curve other places, or perhaps an arc, or sometimes a contour. I think it's called an arc or a contour. I can't remember which in Churchill. I don't know, the terminology varies from book to book, but for Gamelin, a curve, what it's going to be is just something like okay. So there, for example, would be a curve. It doesn't have to be entirely smooth, but it has to be able to, you can join together smooth curves like gamma 1, gamma 2, right? Gamma 3, gamma 4, gamma 5, gamma 6. So if you join together these little paths, right, all together, you get a curve, which is something like a piecewise smooth curve. Now, curves can also be simple, right, or closed. This one is simple. It's not closed. If I wanted to make it a closed curve, what would I do? Yeah, one more line segment, right? And then so, one more line segment, there we go. So gamma 1, union gamma 2, union gamma 3, union gamma 4, union gamma 5, union, why did I do so many? 6, union gamma 7. You could call this whole thing gamma, and gamma would be a curve. Now, oh, goodness gracious. See what the discussion of marketing has done to my mind?
See, I think maybe 3 is a variable and you set 3 equals.
That is true.
Well, then you got the other 2.
You're saying I was using the variable 7 and I'd set it equal to 3.
Yeah.
It's the ghost. Yeah, it is Joe's malevolent intent to corrupt this class as well. Now the trace of gamma in the trace of gamma is simply this. That's just the set of points. This is a set. It's the subset of the complexes. So the trace maybe you could think of as just the set of points, but the curve, the difference between a curve and a path and the trace is the trace has no parameterization. All right. Whereas, yes, sir.
Do you generally use that notation to denote the matrix of the thing that's in it? So would that be the matrix of gamma?
No, it's not the. This is just Gamelin's notation for the trace. It's the set of points. So these gamma sub i's. I'll say gamma sub j. So there's some subset of the reals to the complexes for each one. So these are actually, these are paths. They're parameterized curves. There's an orientation. They have specific domains, and we've joined them together. As you join curves together, I don't want to write down the formulas. It's complicated.
Now, you weren't planning to represent them in the matrix, but could you represent the curves of the matrix?
I probably can represent most anything as a matrix, but why would I want to? I don't know. Because it's interesting. I'm not unsure about that. No offense, but maybe some offense. I don't know. It's just the set of points. The difference between the trace and the curve is the curve has with it a particular choice of parameterization of the point set. So for example, the curve might be, excuse me, the trace of the curve, sorry. You could have like trace of gamma, modulus of z equals to 1. Z, such that modulus of z is equal to 1, right? And that would be, say, the trace of gamma 1, but it's also equal to the trace of gamma 2. And this is by no means, this use of the word trace is weird to me, by the way. I'm just following Gamelin for a minute here. I almost wish we hadn't had this discussion. Oh, well, it's done. So gamma of t, of course, I could do, well, e to the it, right? That's gamma 1. But I could do gamma 2 of t equal e to the 2it. That give you gamma 2. This would be for 0 less than or equal to t less than or equal to 2 pi. This would be for 0 less than or equal to t less than or equal to pi. Same trace, different curves. One is going twice as fast as the other. So really, I would tend to say his curve is a parametrized curve. That's the language I usually use to be more specific. Okay. So what this means in this course is anytime we prove something about a curve, quote unquote, it's really a proof about a parametrized curve, which means that in order to show the definitions we give are well posed, you have to show that the definitions are independent of the choice of parameterization, for example. All right, so let me get on with it here. You can read the definition of reparameterization. You thought about reparameterization in Calculus 3, I hope. Let us get to the definitions that are more interesting. So, although it's debatable whether or not this is that interesting, it's debatable, but it is a necessary definition. Definition. The integral over a curve gamma of p dx is equal to the integral from a to b of p of gamma of t times the derivative of the real part of gamma of t, dt, times dt. The integral of p dy is the integral over gamma, is integral from a to b of p of gamma of t times d, the imaginary part of gamma of t, dt, dt. So I'm defining here integrals. Let me be more specific about what's going on here. So here gamma, you've got some closed interval from a to b, and then here's the complex plane, right? Gamma is some curve. It's going from this point to that point. Here's gamma of a, here's gamma of b, right? So this curve is gamma. And so here's y, here's x, right? Now this p is a complex, it's a complex valued function of the complex numbers. So it's a p is itself a complex valued, it's a function from c to c. And in order for these integrals to make sense, I suppose that p has to be continuous, at least close to the trace, close to the curve, let's say. And so there's slick notation here. It almost looks like there's almost nothing to say here. If you use x and y, right? If we let gamma equal to x plus iy, as is often done, where x and y are functions of time, then what's this definition look like? It just looks like kind of a formal chain rule. So you have, we have p of x of t, y of t, let's say, times dx dt, and this becomes integral from a to b, p of x of t, y of t, dy dt dt. So now, what are the properties of these? This is a new kind of integration. What are the properties? let's see here. You have nice linearity, basically. If you have the complex integral of p plus q dx, and if I've got a constant, complex constant, let's say c1, that's equal to c1 integral of p dx plus integral of q dx, like that. So you have linearity in the usual way, and it's not hard to prove that, right? You just would go up to the definition and sort through the corresponding linearity of those integrals, which are just what? This is actually just an integral from calculus 3, remember? Here I'm actually looking at the integral over a real variable of a complex valued function. I don't know if you guys realize or not that you already know how to do those, right? A complex value is a vector. How do you integrate a vector valued function of time?
By its components?
By its components, right. So let me finish this here and then I'll be more explicit about that. So also, I can do the same with y, right? So you have linearity for both of these kinds of these integrals. All right. Now, but yeah, just to be more explicit about what these are, let me just make a comment just to try to make it a little bit more explicit. For example, not an example of the PDX kind of thing, but an example of the dt sort of thing. Integral of e to the it dt, right? What would that be? Say from 0 to whatever, pi over 2. So this is actually the integral of what? Cosine t plus I sine t dt from 0 to pi over 2. And by definition, you just integrate the real part, and then you do I times the integral of the imaginary part. That's how these are done, right? Nothing too mysterious here. So whatever that is, what is that? Minus sine, no sine. This is 1. So it's 1 plus I think. Yeah. Yeah. So far, so good? Yes, sir.
Are we going to do anything like we did in the last chapter where we had certain theorems like Theodorus theorem and the Cauchy-Riemann equations that show that something is complex differentiable? Are we going to have something like that for integration? Are we going to have to show that something is integratable? Is that the word?
We will have theorems of integral calculus, yes. There will be a fundamental theorem of calculus for complex functions. And eventually we'll get to something called Cauchy's theorem, which doesn't really have a real analog. So it's both the same and yet very different. Kind of like the last stuff, actually. But so I think the answer to your question in short is yes. So in the interest of getting there, let me go on. So what is, you can also look at things, we also have definition, a lot of definitions at the moment. Definition, the integral of p dx plus q dy over gamma is what?
The integral of p dx plus the integral of q.
Yeah, exactly. So it's just what it sounds like. So at the moment, this is a definition. Now, again, keep in mind here, you might be tricked into thinking, oh, I already did this in Calculus 3. That's not quite true because P and Q are complex valued. So let me expand on this. So this would be like integral of gamma P1 plus IP2 dx plus integral over gamma of Q1 plus IQ2 dy. Now here I'm assuming P1, Q1, Q2, and P2. Well, that is very annoying. There's some kind of, I don't know how to describe that.
Screeching.
Screeching sound?
Hissing?
I'm trying to think of what that sounds like being murdered. Nothing comes. I don't know what.
Well, it sounds like the bomb before it goes off.
The bomb before it goes off, maybe. I don't know. Oh, okay. So let me stop using this marker that no one can see on the video. All right. So this, then what, you can reorder this as what? Integral over gamma of what? P1 dx minus, or not minus, oh, yeah, plus q. Plus what? Plus q1 dy, yeah. Plus I times the integral over gamma of what? P2 dx. Q2 dy, yeah. Now, what I have just underlined, put under brackets here, those are honest to goodness garden variety line integrals from like calculus 3, because you have real functions, and if you look at what the integral, the dx integral is, that's exactly the definition of line integral. If you look, it's the, what are you doing? You're multiplying by the velocity in the x direction, the x component, so that is the x component of the work. This is actually, if you sort through the definition, this is the line integral of P1 comma Q1 dot dr, if I use my Calc 3 notation, plus I times the integral over gamma of the vector field P2 comma Q2 dot dr. So, you can interpret then this integral up here, you could interpret as what? It's a complex linear combination of the work done by the P1 comma Q1 vector field plus I times the work done by the P2 comma Q2 vector field along the curve. If you want to give a silly physical interpretation of this particular integral, you could do that. I don't know why you do that, but you could if you wanted to. So typical complex line integral has a little bit more information than a corresponding line integral in the real context, right? Because it's kind of got two real line integrals in there at once, because you have the imaginary and the real components to play with. Es bueno? Okay, all right. So what if you, I just defined this for really a path. How would you do the integrals for a curve where you have more than one of these? What would you do? Yeah, them up, right, exactly. So if gamma is the union of gamma 1 through gamma n, you just take the sum I equals 1 to n of these integrals. You just add up one path after the other. It's in the notes. If you look at definition 3.17, they have the details there. Okay, so we can also define area integrals in the complex sense. So what would the integral over some region, some subset of the complex plane, let's say S actually, of f plus ig dA? Well, that's equal to the double integral over S of f dA plus I times the integral over g dA of S. So this is how we define a complex, the double integral of a complex valued function. It's a complex linear combination of two ordinary real double integrals that we talk about, like in Calc 3, right? What would the partial derivative of a complex valued function? We've already talked about this before, but just to remind you, what's partial x of f plus ig? It's partial y. We have already done these things, but we just do what? Partial f partial x plus I partial g partial x, right? Here I'm taking f and g to be real valued, okay? Nothing terribly surprising here.
Are there going to be things that are terribly surprising, or is it complex?
No, everything is completely boring. Nothing is surprising at all. And you will learn nothing today.
Well, that's not what I mean.
I know. I'm just being mean. But yes, Sharon, as long as I keep talking fast, we'll actually get to interesting things eventually here. So theorem, I do appreciate the question. I'm just being a jerk. So there is a complex valued Green's theorem. So if we let p and q be complex, okay, complex valued, then the integral of p dx plus q dy. And let's suppose that gamma is the boundary of some region S. So gamma is a simple closed curve which bounds some simply connected region S, right? Remember, that's where Green's theorem happens. For a simply connected region, we have Green's theorem. So what was Green's theorem? Do you guys remember? It connects this line integral to a corresponding double integral, right? What was the double integral? Okay. All right. Well, partial q partial x minus partial p partial y. These things we should have learned in Calc 3. But it's okay if you don't remember.
There was too much snow last year.
Too much snow last year. I think the math is still there. I hear you, though. Okay, so the way to prove this, right? Well, there's a proof in Gamelin which is actually nice and constructive. He proves it for a triangle, and then he argues that you can take a simply connected set, or maybe a star-shaped set, and break it into triangles, and then add up the values on each little triangle, and you get Green's theorem on the whole thing. I'm going to be lazier. I'm going to say, hey, I proved this in Calculus 3, so I'm going to use what I know from Calculus 3 to prove this. So my proof is a little bit more boring in the following sense. So my proof is basically just this. If I take p dx plus q dy, what do I have? Oh, this is over S, right? Okay, sorry. Well, this is the integral of p1 dx plus q1 dy plus I times the integral of p2 dx plus q2 dy, right? That calculation I just worked out a second ago, and I shouldn't have erased. And so, you know what? I just apply, I know Green's theorem for real integrals already, so I just apply the ordinary Green's theorem on the real component and the imaginary component here separately. 2 applications gets it for me, I'm done. So this is the integral over S of partial what? Partial q1 partial x minus partial p1 partial y dA plus I times the integral over S of partial q2 partial y minus partial p2 partial x dA, right? And then what do? Just rewrite it as a single double integral, right? That's integral over S of partial x of, well, q1 plus I q2. Oh, don't let me get away with that. What's wrong over here? Yeah, I think I said x, but I wrote y. I'm an idiot. Let's see here. So partial x of q1 plus I q2 minus partial y of p1 plus I p2. But hey, what's that? That's precisely this, right? Because q is equal to q1 plus I q2, and I'm saying p is equal to p1 plus I p2. And there you have it, complex Green's theorem. Okay? You're like, well, I didn't see a proof of Green's theorem in Calculus 3. Well, I think that's not probably right. I think you probably did see a proof of Green's theorem in Calculus 3. That's okay. That any Calculus 3 should have a proof of Green's theorem, at least if you took it here. Oh, well, let's suppose that you didn't have a proof of Green's theorem in Calculus 3. At some point this semester, I will prove Green's theorem in Calculus 3. When that happens, I will send you guys a link. What's that?
Can we just come and join your class?
I mean, yeah, sure. We got room.
Let us know.
Anyway, the proof of Green's theorem in Calculus 3 is kind of somewhat immaterial to what we're doing in the larger program like this chapter. So the interesting part of this chapter doesn't have much to do with the proof of Green's theorem, right? Green's theorem is just something we want to use here mostly. So I'm skipping over some interesting examples in the notes. You should read them and try to internalize them. So if h is a complex valued function, if h is a complex valued function which has continuous real partial derivatives, so h sub x and h sub y, all right, then the differential, we define dh, the differential of h, to be partial h partial x dx plus partial h partial y dy, right? Remember this, the total differential? And for us, we'll just think of it as a formal symbol for now. I mean, that works. You can ask me what it is. I can give you different answers. But we'll just think of it as a formal symbol for the moment. That said, a differential form is said to be exact. So we say, I mean, that's a differential form, right? So we say a differential form let's say p dx plus q dy. All right, there's my form. Let me give this thing a name. Let me call it omega, just to give it a name, just some name calling. This is exact. What does it mean for omega to be exact? And exact is, we must be careful. When we talk about exact forms, we have to talk about domain. Domain is crucial. So I should say exact on U, a subset of the complexes, all right? If what? What does it mean for it to be an exact form? If there exists H, such that what? dH equals to what? Omega. So it's an exact form if the form can be attained by just the total differential of a function. Okay? And that has to happen at each point in U. So I'll just put in parentheses on U. If it fails at even one point in U, that's enough to say it's not exact, all right? 1 point makes a difference, actually, here. And so finally, here's the theorem Michael is asking me for. Theorem. If you have a piecewise smooth curve from A to B, and if h is continuously real differentiable near gamma with dh equals to p dx plus q dy, then we have the integral of p dx plus q dy over gamma. All right, if this is equal to dh, all right, then this is simply equal to h of b minus h of a. And here, of course, I'm supposing that the curve goes from point P to point A. So point A to point B, rather. So here's B, here's A, gamma is some curve, I don't know. All right. Actually, I'm advocating, maybe it's not a single path. It could be, it could be it could be piecewise smooth, right? So you might need lots of paths joined together at points of where you could have a lack of smoothness, right? You could have kinks, and it could be jagged, right? I mean, the curve could look something like, I don't know. It could look like this. I mean, that's a possible curve.
Like a dinosaur.
My point is, it can have lots of whatever. But then I don't want to do the proof of this for that, all right? Basically, if you can prove this for a single little path, little lines, little curve in here that has just one parameter domain, then you just add them together. And then at the joining points, you get the starting and the ending canceling until you're just left with the final initial point and terminal point. Okay, so the proof is what? So I'll just do it for a single thing, but here you have gamma p dx plus q dy. So that's the integral, say from a to b of, how's it go? It goes p of gamma of t times dx dt plus q of gamma of t times dy dt, right? All dt. But you know what? That's exactly that's the chain rule. That's what you get from, sorry. So this is, one more step, I guess I gotta jump in the gun here. So that's partial, excuse me. That is partial h partial x dx dt plus partial h partial y dy dt. How do I know that? As dh is equal to pdx plus q dy, right? Since dh is pdx plus q dy, that means that partial h partial x is equal to p, and partial h partial y is equal to q. You guys got me? So then that is what? Well, that's the integral from a to b of d dt of h of, gamma of t dt. And h is complex valued. Fine, you got me. It's true. But there's a fundamental theorem of calculus for vector valued functions of a real variable, which says that you can just, there's a theorem from calculus 3 which tells me that this is in fact just h of gamma of b minus h of gamma of a. The theorem I'm referring to in calculus 3 is that the integral of dr dt is r of t1 minus r of t naught. If you go from t naught to t1, there's this, you apply the ordinary fundamental theorem of calculus at each component, and then they piece together to give you this total change theorem for a vector valued function of a real variable. So I'm just applying it in the n equals 2 case here. And of course, that's what? That's h of b minus h of a, all right? All right. Questions? What is the meaning of life? I don't know. To glorify God, I suppose. Let's see here. 42. All right, guys. I need to get the bigger picture here. If I keep writing, I'll never get to it today. So our ultimate goal here is to try to understand the connection between a differential form like pdx plus qd. Yes, sir?
The video. How do I get it to the screen?
Oh, you just,
Edit this out.
oh yeah, edit, haha, funny. It's just like this.
Will that be a little tiny?
Well, you can, it vertically pans. I spent $50 whole on that tripod. Okay, so I have defined a differential form pdx plus qdy being exact, right? Exact means it's the differential of a function. You can also talk about a differential form pdx plus qdy. Let's call it omega, all right? There are like 4 competing terms that we need to understand how they relate. So we have omega equals pdx plus qdy, right? There's exact. That means that dh is equal to omega. There's closed. Closed means that, well, I don't know what that means yet. you can talk about path independence. Path independent. So that means that the integral over gamma 1 of omega is equal to the integral over gamma 2 of omega whenever you've got omega 1 and omega 2, gamma 1 and gamma 2 being two paths between the same terminal points, right? Path independence. Closed, exact, path independent. What's the other one? Harmonic. So let's see here. And so what we're actually trying to do here, believe it or not, is to understand the connection between these different animals. Come on. I have it plugged in. It should be working. What's going on in here? Really? Very annoying. All right, so we got exact. What did we just show? If it's exact, what do you get? This theorem right here, right? So does exact imply path independent? Look at this theorem. If it's exact, that means it's the differential of something. It has this form, right? And so what this theorem says is that the value of the integral of the form along the curve depends only on its terminal points. Its endpoint minus its initial point, right? So any two curves which go from A to B, same integral, right? So yes, exact implies path independent. All right. What else? There's another theorem. You can also talk about the integral. There's another notion here. Sometimes we like to throw around. What's the word for this? I forget the word, but basically the integral around loops is equal to 0 for all loops. And this is all happening inside some subset of the complex numbers. All right. So why would does path independent imply integral around loops is 0? Well, what's a loop look like? It looks like this, right? Roughly speaking. So you take any 2 points on the loop that you like, right? And if the whole loop, you can write the whole loop as like something like gamma 1, right? And then there's a gamma 2 over here, right? But you can reverse gamma 2, disoriented, if you will, go the opposite way, right? And you call that minus gamma 2. Well, the definition of the definition of the integral we looked at today has the following property. If you reverse the curve, you get, a minus when you pull it out and put it back, right? So if we have that the integral around the loop of omega is 0, that implies that the integral along gamma 1 of omega plus the integral along minus gamma 2 of omega is equal to 0. But that implies that the integral along gamma 1 of omega is equal to the integral along gamma 2 of omega. In other words, if you have integral around loops to 0, you can imply path independence because you can take the loop and break it up into two paths and they have to add up, right? And vice versa. If you take two paths, you can reverse this. It's a if and only if, right? If I have path independence, I can get loops going to 0 as well. So that's another way we can look at this problem. Lemma 3.2.6. Let P and Q be continuous complex valued functions in a domain D. Then the form omega is path independent if and only if it's exact. All right. So I've already showed you that exact implies path independent, but the converse direction is harder to prove, right? How do you prove that if it's path independent, it must be exact? Do you understand the question? The difficulty? Here's the current problem. Why does path independent imply exact? And so path independent means that the integral of omega over gamma 1 is equal to the integral of omega over gamma 2 for all possible paths, gamma 2 in some domain. So we're talking about some connected region, you know. So we got two paths, gamma 1 and gamma 2, and we get same integrals, right? On the flip side, exact, what's that mean? That means that omega is equal to dh on, you know, the whole thing, right? On the whole region. I don't know if this projector's broken or something. Should have picked it up. Oh, thank you. All right, so what I'm trying to help you guys to wrap your mind around here is these different ways we have of, thank you, of looking at, we have path independence, integral around the loop is 0, you know, again, exact, it's the form is the exterior, the total differential of a function h, complex function h. And then 4, given an additional condition that D is star-shaped, you can show that it's closed on D. Closed on D is the condition that partial yp is equal to partial xq. What does that have to do with anything we've talked about today? This definition of closed. Closed is, here's the definition of closed, is that the y derivative of the x component is equal to the x derivative of the coefficient of the dy component. Remember we wrote earlier? Remember Green's theorem? This would make the area term in Green's theorem be 0. So, I mean, you could define a closed form as one which makes the area term on the Green's theorem formula be 0. All right, so going back up here. So it takes a little work, right, to establish those various equivalences. I'm trying to go back to the first one. So here it is. Lemma 3.2.6, if p and q are continuous complex valued functions on a domain D, then p dx plus q dy is path independent if and only if it's exact. Again, exact implies path independent, piece of cake. We already proved that. The other direction, though, we need to look at. So what you do, the whole question of how to show it's exact, that means that you have to somehow construct a function h so that the differential of h gives you back p dx plus q dy. All right? In other words, you have to find an h such that partial h partial x is p and partial h partial y is q. That's all that really means. So what is this h? This is how you define it. Because it's path independent, you can just pick some point in the domain, right? And this makes sense. If I tell you the initial point and I tell you the final point of the line integral, that's well defined if we have path independence, right? It doesn't matter which path you take from a to z, that has a single value. So this is a function of z. Path independence gives you that this is single valued. So this is our proposal. H of z is equal to that. Now what do I have to show? I have to show that partial h partial x is equal to p, and I have to show that partial h partial y is equal to q. All right? So what you do is you fix a point, A is like a reference point, and then I fix a second point B, and x naught, y naught. I want to study the partial derivatives of h at the point x naught, y naught. All right? So the picture over here is come on. Here's the picture. So I'm trying to figure out what's the partial derivatives at that B point. All right? So this point B. The point B is x naught, y naught. x naught plus I y naught. And so I can, to figure out the x partial derivatives, I can look at the one, like I allow x to vary holding y fixed. That's going to tell me something about the x derivative. And if I let x be constant and y fixed, that gives me the path 2. So I think this is, the green is gamma 1, if I remember right. Gamma 1 goes from so here's h of x naught plus I y naught is this. So you can break it up into the integral along gamma plus the integral along the green part, right? That's, if you have two lines connected, it's additive. But the gamma 1 is very boring. It has x equal to t, and it has y equals to, y is fixed, right? Y is equal to y naught. So when you look at along gamma 1, dy is 0. Dx is dt, right? So this integral just becomes integral from x naught to x of p of t comma y naught dt. And then you've got this integral from gamma, this piece over here, which is that integral. Okay, so then if I want to calculate the partial derivative with respect to x, I can use that expression to do it. Since gamma has no dependence on x in this setup, since gamma has no dependence on x, when I partial differentiate this with respect to x, that's just 0, and you're just left with this piece. But hey, if you take the partial derivative of an integral with a variable bound, fundamental theorem of calculus part 1 tells me that's just p, and I plug in x like that. And so there you have it. Partial h partial x is equal to p. And then if you look at the other corresponding argument along the y, the vertical strip, that gives you partial h partial y is equal to q. And so that's how it works. Because of the path independence, we can define h just by this integral. And there's interesting physical significance to this. What we're doing, what h really is like a potential energy function, right? And that point we picked A is like where we're saying there's 0 potential energy. Not quite accurate. Potential energy, you need a minus sign in for reasons of physics, but this h is what I would call a potential function for the form p dx plus q dy. All right. So there you have it. I mean, there's also a question of uniqueness, but that's dealt with by, if you had two forms, h1 and h2, then you can prove that the difference of them has gradient 0. But since we're on I'm assuming connected, right? So if the gradient 0 on a connected set, remember we proved that it has to be constant. So if it's 0 at one point, it has to be 0. I mean, so you get uniqueness from this little argument down here. So what I'm doing here in section 3.2, really you should have seen these arguments in calculus 3 just for real valued vector functions. Actually, all these arguments are just duplicates of the things I would say in calculus 3 anyway. I talk about path independence of vector fields. I talk about integrals around loops of vector fields, right? I wouldn't call the vector field exact. I would call it conservative. But what's a conservative vector field? It's one that can be obtained by the gradient of a function. Well, that's exactly the same as this exactness condition if you look at it, right? Think about it. P dx plus q dy is equal to dh. What's that mean? Well, what is dh is basically just the gradient of h dot dr. So if you think through it, this exact condition is exactly the same as the conservative vector field condition from calculus 3. Anyway, I will spend more. It always takes me longer than I want to spend on this section because there's a lot in here. Next time I'll explain to you what star shape does and the issue of the closed and star shaped. Now, what I want to get to, where I feel like it starts to get genuinely complex in here, Sharon, is over here when we get into section 3.3 and we get this theorem. If u is a harmonic function, its differential is closed. So there all of a sudden we get this connection between the closed exact and the harmonic. As you know, the harmonic is tied to the complex differentiability, right? So if I have u plus iv, u is harmonic. That will then say that the form that corresponds to u is closed. That particular form is closed. So, and then later in this chapter or next chapter, we get Cauchy's theorem, which is just radically different than anything you've seen before. It's It's really different. Oh, so anyway, you can cut off the camera. I do have your